Okay, so this is homework 6, problem 1. And so we're given that the joint density function of x and y is equal to bxy for x 0 is less than y is less than 1, and 0 otherwise. And so for part A, we're asked to find b such that this joint density function will be true. And so in order for this joint density function to be true, the area of this joint density function over its bounds has to equal 1. And so since we know that the bounds of x is from 0 to y, and then the bounds of y would be from 0 to 1. So it will be a double integral of bxy from 0 to y dx and 0 to 1 dy. So it's 0 to 1 dx because we want to integrate out the value of x. So then when we integrate y, it'll give us a number. So when we integrate bxy, by can come out since we're integrating first with respect to x. It'll be x squared over 2 from y to 0, and that gives us y squared over 2 when you plug in y. It'll be 0 for when you plug in 0. So then we get b times y cubed over 2 dy from 0 to 1 is equal to 1. And so we integrate that, we get b over 8 is equal to 1, and b is equal to 8. So for part A, b is equal to 8. For part B, we're asked to find and sketch the marginal density functions, that being fx of x and fy of y. So in order to get fx of x, we have to integrate fx and y over the bounds of y to find x. And so the bounds of y will be from x to 1. So it's x to 1 of 8xy dy from x to 1. And so when you do the integration, you end up with 4x minus 4x cubed. And that graph over the bounds of x, which is from 0 to 1, looks similar to to a half circle. So it's 0 at 0, and it is equal to 0 at 1. Had we continued this graph past 1, the line would dip below y equal to 0 and continue on negatively. Okay, for fy of y, we integrate fxy over the bounds of x, which is from 0 to y. So we're eliminating the x component to make so f of y will be in terms of y. And so we get fy of y is equal to 4y cubed, and 4y cubed looks like that graph below. Okay, and that's part B. For part C, we're asked to prove or disprove that x and y are independent. And x and y is independent if the marginal density function, the joint density function of x and y is equal to the marginal density functions fxx times fy of y. And as we can see clearly here, 8xy, which is the joint density function, is not equal to the marginal density function of x times the marginal density function of y. So therefore, these two variables are not independent. For part D, we're asked to find the expected value of x, the expected value of y, and the expected value of xy. And so the expected value of x is simply just the integral of x times f of x over the bounds of x. And so the bounds of x is from 0 to 1. So it's 0 to 1 x times f of x will be found to be 4x minus 4x cubed dx. And when we integrate out that, we get 8/15 for the expected value of x. For the expected value of y, it's simply just the integral of y times fy of y dy over the bound of y. And similarly, the bound of y is also from 0 to 1. And so when you integrate that out, you get 4/5 for the expected value of y. And so the next part we'll be doing the expected value of xy. So the expected value of xy is just equal to xy times f of x and y over the bounds of x and the bounds of y. And so similar to how we found b in the first part, the bounds of x will go from 0 to y, and the bounds of y will go from 0 to 1. And when we integrate that out, we end up getting 4/9 is our expected value for xy. For part E, we're asked to prove or disprove that x and y are uncorrelated. So the formula for correlation this is equal to, so the correlation of x and y is equal to the covariance of x and y divided by the square root of the covariance squared of x times the covariance squared of y. Also, covariance is equal to the expected value of xy minus the expected value of x times the expected value of y. So obviously if covariance is equal to 0, then correlation will also equal 0. And so we simply just plug in our values for the expected values of xy, x, and y, which we found before. And so the expected value of xy is 4/9 minus the expected value of x times the expected value of y, which is 8/15 times 4/5, which, as you can see, clearly does not equal 0. Covariance can also be a negative number. So as long as it's not 0, therefore, the correlation has a non-zero value, and therefore these two random variables are correlated. For part F, we are asked to find and sketch the conditional density functions of fy given x and f of x given y. And so f of x given y is simply just f of x and y divided by f of y. So that we had before, so f of x and y is equal to 8xy, which we found in part 1, divided by 4y cubed, which we found in part B. And so that gives us, 4x parentheses 1 minus x squared, which we found in part B. And so that gives us 2y over 1 minus x squared. And so when you want to graph this, you would ask, how would we graph this? So since it's conditional, it's for f of y given x. So we're given x. So let's choose x, which will make this plot easy. So in this case, let's choose x is equal to 0. And so for x equal to 0, the plot of fy of x given x equal to 0 is equal to simply just to 2y. And so we would plot from 0 to 1, which is the bounds of y, over 2y. And we can see that the area under this curve will equal 1. So therefore, this is a valid density function as well. Similarly, f of x given y is equal to f of x and y divided by f of y, which is equal to 2x divided by y squared. And so graphing that is a similar process. We choose a y such that f of x given y is easy to plot. And so a simple y would be, let's say y is equal to 1. And so we get 2x. And so 2x over the bound of 0 to 1 also has an area of 1. And so f of x given y is also a valid density function. Finally, for part G, we are asked to find expected value of big Y given small x, the expected value of big Y given big X, the expected value of big X given small y, and the expected value of big X given big Y. And so the expected value of big X given small y, or when big Y is equal to small y, is equal to the integral of x times the conditional density function of x given y. And so we found this in the previous part. So we know that the expected value of x given y, the density function of x given y is equal to 2xy squared. So we plug in 2xy squared times the x, which is part of the formula, over the bounds of x, which is from 0 to 1. And so for the first part, we can take out 2 over y squared because it's with respect to x. And the integral of x squared is equal to 1/3 from 0 to 1. And so we get a value of 2 over 3y squared for the expected value of x, big X given small y. Similarly, the expected value of big Y given small x is equal to the integral of y times the density function of y given, that's the joint density function of y given x dy. And so we know that the joint density function of y given x is equal to 2y over 1 minus y squared times y over the bound of y, which is from 0 to 1, and we get 2 over 3 times 1 minus x squared for our expected value of big Y over a big Y given small x. For the expected value of big X given big Y, it's simply just the expected value of xy divided by expected value of y, which is equal to simply So we know that the expected value of xy is equal to 4/9. The expected value of y is equal to 8/15. So 4/9 divided by 8/15 gives us 5/6. Finally, the expected value of y given x, so that should be a y. It's a y given big Y given big X, is equal to the expected value of x times y divided by the expected value of x. So it's 4/9 divided by 4/5, and that gives us 5/9 for the expected value of big X given big Y. And that is problem 1.